Alright, welcome back to the second video on COP and cooling load calculations. In today's class, we shall be solving a question using the steam table. As you can see, this is a steam table. I sent you guys a copy of this steam table. Alright, let's look at our first question. It reads, an ideal vapor compression refrigerant cycle operates at steady state with refrigerant 134A as the working fluid. Saturated vapor enters the compressor at negative 18 degrees Celsius and saturated liquid leaves the condenser at 28 degrees Celsius. The mass flow rate of refrigerant is 10 kilogram per minute. Determine A, the compressor power in kilowatts, B, the refrigerant capacity. As you all know, that is the cooling load, and C, the coefficient of performance, in this case the refrigerant. All right, so the first thing is to represent this information on a TS diagram. Draw a TS diagram. All right, this is point 1, point 2, 3, and 4. Right, at the compressor, which is at this point, the temperature is negative 18 degrees Celsius. Then at the condenser, the temperature is 28 degrees Celsius. So most times you'll be asked to represent the information on a TS diagram. All right. Step 1 is to find the enthalpy at point 1, point 2, point 3, and point 4. Now, if you remember in our first video, I was saying that at stage 1, the enthalpy is gaseous. At stage 2, it is also gaseous because the compressor compresses the low vapor refrigerant to a high vapor refrigerant. At stage 3, the refrigerant becomes a fluid or a liquid. Then at stage 4, it is a liquid. All right, now from the question, it says the vapor enters the compressor at negative 18 degrees Celsius. So at 18 degrees Celsius, we can find our enthalpy 1. So at 18 degrees Celsius, my H1 is, now to get your H1 at 18 degrees Celsius, we use the steam table. Now this is the steam table. As you can see, is a steam table for refrigerant 134A. Okay, to get our H1 in negative 18 degrees Celsius, we trace it to Hg, because at H1 the refrigerant is gaseous, so it is 236.53. 236.53. Come back to my notebook. This 236.53 kilojoules per kilogram. All right. Now at point 2, the refrigerant vapor is condensed at 28 degrees Celsius. All right. So the refrigerant gas leaves the compressor and enters the condenser where it is condensed. All right. So at point 2, we use the temperature at 28 degrees Celsius. So at 28 degrees Celsius, we can find the value of H2 gaseous. Now we go back to our steam table. At 28 degrees Celsius, which is at this point, we find the corresponding value of Hg, which is 262.50. This 262, it is 262.50 kilojoules per kilogram. All right, so that is H2 gaseous at 28 degrees Celsius. All right. Now at point 3, at same temperature, which is 28, all right, the refrigerant gas has been condensed to liquid. So we can also find H3 at same temperature, because the temperature at this point did not change. So we can also find H3 at 28 degrees Celsius. All right. In this case, the enthalpy becomes liquid. All right. So go back to our steam table. At 28 degrees Celsius, we find the corresponding enthalpy at saturated liquid, which is 88.61, is 88.61, 88.61 kilojoules per kilogram. All right. Now, if you remember, in my first video, I was saying that the enthalpy at point 3 and at point 4 are the same, because in this phase there's no heat loss and there's no work done. So H3 fluid is equal to H4 fluid. So H4 becomes 88.61 kilojoules per kilogram. Now these are the values that you will need to solve the questions. But remember that you were given a mass flow rate of 10. Mass flow rate was given as 10 kilogram per minute. All right. Now we can solve by finding the compressor power. All right, in kilowatts. Okay. All right. So now we are asked to find the compressor power in kilowatts. Now, if you recall, the compressor power is the work net, which is equal to the mass flow rate times the H2 gaseous minus H1 gaseous. Alright, what next is to log in the values. Okay, so we now have the mass flow rate is 10 kilogram per minute times our H2 gaseous is 262.50 is what? Is 262.50 minus our H1 is 236.53. Our H1 is 236.53. As you can see, they are all in kilojoules per kilogram. All right, what next? We now have 10 kilojoules per minute times 262.50 minus 236.53. That gives us 25.97 kilojoules per kilogram. Alright, so we now have 10 times 25.97, which gives us 259.7 kilojoules per minute. Now we are asked to convert these to kilowatts. To convert these to kilowatts, we multiply by 1/60. So it becomes 259.7 times 1/60. That gives us 4.3 kilowatts. So this is the compressor power of the system. Now for the B part, we are asked to find the refrigerating capacity in tons. Now this is same thing as cooling load, which is QL. Now QL is giving us mass flow rate times H1 gaseous minus H4 fluid. Alright, so we can log in the formulas or the values. For the mass flow rate, it's giving us 10 kilogram per minute times our H1 gaseous was given from the table as 236.53 minus our H4 fluid was given us 88.61 kilojoules per kilogram. So we have 10 kilogram per minute times 236.53 minus 88.61 gives us 147.92 kilojoules per kilogram. Alright, so what next is the kg, cancels out the kg here. So 10 times 147.92 gives us 1479.2 kilojoules per minute. Now we are asked to leave our answer in tons. Now if you remember, in my first video I said that we can convert kilojoules per minute to tons by multiplying by 1/211. So I will convert these to tons by multiplying 1479.2 times 1/211, and that gives us 7.0 tons. That is our answer for the refrigerating capacity or cooling load. Alright, for the last question C, we are asked to find the coefficient of performance. In this case, for a refrigerator, it is giving us COP of a refrigerator is equal to the cooling load, which is QL over the work net. Now, what is the cooling load? The cooling load was given as H1 gaseous minus H4 fluid over the work net is given as H2 gaseous minus H1 gaseous. So from the table, our H1 is 236.53 minus H4 is 88.61 divided by our H2 gaseous is 262.50 minus H1 gaseous is 236.53. When you subtract this, you get 147.92 divided by 262.50 minus 236.53 gives us 25.97, and when we divide that we get 5.6 5.7. 5.7. So this is the coefficient of performance of the system. 5.7. As you can see, COP has no units. All right. Now this is the solution to the example. All right. So I will like each person to look at the example on the slide. I want each student to look at this question. There are some mistakes in the solution. All right. There are some mistakes with these values. So I want each student to solve this question and point out to me the mistakes that you can identify in the solution of this question that was done on the slides. All right. So guys, if you have any question or any challenge with using this team table, feel free to send me a message or leave a comment in the comment box, and I promise to respond immediately. Thank you very much for your understanding. God bless you and have a great day. Stay safe and continue to wash your hands and try as much as possible to sneeze in your sleep. Bye bye and have a great day.